The following program is brought to you by Caltech.
Okay, well, I'm Stephen Kurtin. I was a student of Carver's PhD student, starting in 1967. I actually got here in 1966, but didn't start in earnest with Carver until 67, if memory serves. And there was a group here, an interesting group. Tom McGill, who was subsequently a professor here, has passed away. Jerry Parker, my office mate, one of my office mates, graduate student office mate. When he was getting ready to graduate with his PhD, I remember him asking my wife whether he should go to take the offer at Bell Labs or at this little startup in the Bay Area. And my wife Barbara counseled the startup because if it didn't work, he could always go to Bell Labs. It was a little company called Intel. John Kaywood, Mike Anthony. I was hoping Mike would be here, and Bill Watrous. I think I'm the only representative of this era that's here. At any rate, I want to talk about three different sorts of things. It's supposed to be about devices. I assure you it will not be. Hopefully it'll be more interesting. I want to talk about seizing the moment and serendipity. I want to talk a little about tunneling, and by the way, Dick stole some of my slides, and starting a sort of computer company. So we start with Meharry's, which in the interest of old times, I went with my wife Barbara, who's in the back there, to lunch today, just for nostalgia's sake. And it was a place where we used to go for lunch every once in a while, particularly on Fridays. And Carver would show up. My wife was working at Stanford Research Institute and come and talk about things. And from this, I think Carver liked the Huevos Rancheros a lot, as I recall, and I think that has something to do with our trying to grasp this Nobel opportunity. And what happened is, and this is sort of the prehistory of this whole thing, I presume that most of you have heard of, but probably didn't much follow polywater. So here's a very, very brief history for you. This Russian guy named Fedyakin, who was really a provincial, was studying this stuff that he could make by hanging capillaries over a tray of water and waiting months. And he'd get this goo in the capillaries and take it out. And it was strange stuff, and that's about it. He just called this stuff anomalous water. Well, it came to the attention of a guy named Deryagin, who was not so provincial. He was actually director of the Laboratory for Surface Physics in Moscow. So people listened to this guy. And he published these crazy numbers, boiling point of 150 degrees C and a freezing point of minus 40 C. And he presented this to the Faraday Society, which is, kind of old line science. And it began to get some attention. But really, this thing lit up in June of '69 when Lippincott, who's a US guy and highly respected spectroscopist, published a paper in Science with infrared spectrum showing, by implication, molecular bonding that was totally unlike that of water. And he went even further and said, this is polymerized water, it's polywater. And this was sensational stuff. I mean, it was it captured the interest of the scientific community, even the military community was captured. Some people were concerned about Ice 9. You could polymerize the water in the world and eliminate life on Earth. We missed that. But the whole idea that water, which is such common stuff, could be different was just sort of revolutionary. And that idea came to me and Carver mostly over lunch. Barbara introduced it. And you can see it was just the same day that it came out in Science. We went to lunch and Barbara mentions polywater. And one of the questions, of course, is what is the structure? The infrared spectrum only kind of gave a hint of what the structure might be. And Carver had this great idea that maybe we could contribute to figuring out the structure, and surely that would be worth an honorary mention in the Nobel Prize that this guy Lippincott is bound to get. So game on. Well, we were focused on studying current flow in semiconductors and insulators, contact properties. So we had the ability to characterize really small samples. And one of the things about polywater is it took so long to make, so hard to make. People had only these really tiny samples, sub-microliter kind of samples. And we were good at making a certain kind of measurement that would maybe give some insight into the structure, and we were hoping for that. And Barbara had access to aqueous wet chemistry, and she was cute, so she could talk her friends into making this stuff, which they did. And you know, this water is very well-known stuff, so it was kind of important. At any rate, we made these measurements of dielectric constant, and they were absolutely amazing. I mean, if you look at water dielectric constant, basically independent frequency, and it's something like 80, and it's known to about 27 decimal places. I mean, it's very well known. And we get this thing, it's 10 to the 7th. Well, it's a little bit bigger than 80. It's kind of frighteningly bigger than 80. The Nobel Prize is right within reach, right? Just right. So we turn up the frequency a little bit, and the dielectric constant drops. And we turn up some more, it drops some more. Finally, you get up to about 10 megahertz, and it's pretty close to that water. No idea. Well, never seen anything like this, never heard of anything like this, had no idea. I mean, not only is polymeric water, but it's amazing. I mean, it's got these properties. I'd never seen anything like it. So those days, they actually had a library here at Caltech, and we went over to try and understand what was going on. And there was the proceedings of the IEEE, or actually IRE, I think it was called at the time. And we discovered something. We discovered that properties like this were actually known, but they weren't known for pure materials. They were known for suspensions, where you had tiny particles, like mud or almost homogenized milk, where you had little particles of cream in the water. And so you had an interface where you could shove charge in between the water and the particle. And so it was frequency dependent, and at low frequencies you could shove in a lot of charge. And you got this ridiculous curve, and all of a sudden made sense. So since I just learned about this idea of a new way of thinking, okay, makes sense. You see this thing, it's probably a suspension. Well, along the way, I had the good opportunity I was a Hughes Foundation fellow, so at Hughes Research, Dick finally used to come out and give talks. And I explained to him about this polywater thing, and I explained to him that we thought maybe there wasn't any polywater, and just like that, just like Dick Fromm used to, he said, you gotta be right, because if there was polywater, there'd be an animal that drank water, shit polywater. No animal, no polywater. So, get into my Dick Feynman story. At any rate, science, Carver just mentioned about knowing about how to get things published. Science didn't want to hear about it. The notion that polywater, because they'd broken the polywater story, the notion that polywater might not be real, the pushback was unbelievable. And Carver was really the guy fighting that battle, trying to get science to publish this thing, trying to get them science. And you know, we were a little bit hesitant and so on. We couldn't get science to publish. Finally, one other paper came into Science that said the same thing we did, and Science did publish this in this article in March of 70, and it was picked up by this blog, the New York Times, and they wrote this thing up about what we were doing and say, hey, these guys are skeptical, but if you read the yellow part, it talks about the establishment, which really means the guys who had sponsored polywater, resisting and saying, your polywater may be contaminated, ours isn't. You know, you haven't got the right stuff. Okay, the spectrum's the same, but it's not the right stuff. And this was the beginning of the end. It just caved in on itself. It really was nothing but polycontamination, little particles of particulates in the water. And it makes a lot of sense because you had this water sitting for a long time in capillaries with leaching stuff out of the walls and making these little particles. So it was really just a great adventure, started over lunch and going forward to ruining a few guys' reputations. And damn it, we did not get the Nobel Prize. Not any of us. Okay, so much for that. We had a primary mission, and this was a really kind of a interesting approach to technology that Carver had come up with. He was interested in the fundamental aspects of current flow, and some work had been done, some really good work by a guy named George Lewicki, who came before me on tunneling currents in aluminum oxide. And the idea was you'd take a piece of aluminum and you'd grow the oxide on the aluminum, and then you put on some contacts, you could grow the oxide very thin, measure the current going through there. The deficiency of it was you didn't really know what you had because the oxide wasn't stoichiometric. It grew and it changed its properties as it grew off the substrate. Carver had this idea, and he had a very gullible student that he could talk into doing this, that you could have a layer compound, think graphite, but this isn't graphite, it's gallium selenide, and it's a structure like that. It's very tightly bonded within the layers, but very shallow bonding in between the layers. that you could characterize this stuff in the bulk, and then you could peel it. So you ended up with a very thin layer of this stuff, and you knew what you had because you peeled down this sandwich of lots of layers. And because the layers were only a 10, 12 angstrom kind of thing, you ought to be able to peel it down to a few tens of angstroms, thin enough to tunnel through, so you could actually know ahead of time what all the properties were of the structure that you made, calculate what the currents ought to be, and see if you could do real science, see if you could predict the currents you were going to get from the real numbers. I mean, the notion that you can take anything and peel it down to about 20, 30 angstroms, like, good luck. Amazingly, it worked. We were able to do it. And resulted in this paper, which became fairly well known because we really were able to characterize what was going on. Tom McGill, who I mentioned, was heavily involved in doing the calculations, which were pretty substantial for figuring this out. Particularly, there's this thing called the EK relation in the material, and when you have some data, translating that into the EK relation is a lot of computation, and Tom McGill computed that. At any rate, the structure, I don't want to, I mean, this is Caltech, but I don't want to bore you with it. The structure is two different metal electrodes with this insulating layer, and these are the various parameters that characterize this kind of structure. So it's called MIM, metal insulator metal, and the insulator here is that thin layer of gallium selenide. And this is one of the curves I really liked. So this was, as it were, calculated ab initio, forward direction, reverse direction, and the agreement between the calculations and the data was at least fairly good. So we've talked about doing a little science on a special kind of insulator, gallium selenide. And by the way, you could make the structure thicker so that tunneling no longer dominated, and you could look at other kinds of contact-limited current flow. And we ran out the whole deck there. We did actually thermionic emission and TF emission and tunneling and the whole deal. Well, along the way, because we were trying to have some fun, it kind of became clear that calculation was difficult because Caltech had a computer center, and it had a computer which Carver, I don't know if he still calls him an earthworm, but he did at the time. And the idea was garbage in, garbage out, and you'd run over there, you submit your deck. You go back in 3 or 4 hours, come back and say you forgot the job card. You put in the job card. You come back 6 more hours, and you left out a comma, and you go back around and around. Never compute. And it was really tedious. And so Carver and I began looking into the possibility of acquiring a computer for the group. And computers in those days weren't like what you think of today. It was a box, and there was electronics in it, and there was no display, and there was no keyboard, but there were switches. On the front panel, there were switches, and there you could put in an address in binary, and you could put in data in binary, and then you could load that into the register. Then you do the next one. That was called booting up, and that's the way it worked. And they weren't very powerful at all, and there was no inherent kind of infrastructure. So these things all computed in fixed point. And I subsequently heard from Denny Hillis that God computes in fixed point. And he may be right, but it didn't help us any because we wanted to put in these numbers with big exponents, and fixed point weren't going to get it. So we really were frustrated. I remember driving down to a place called General Animation with Carver and looking at this computer. We're just scratching our head and saying, what do you do with this? I mean, it's not going to work for us. But along the way, we had this idea that maybe you could take electronics and make a computing device which was tailored to do a specific job. So it wasn't general purpose at all, very specific, very much built around the task to be done. And that resulted in our actually starting a company. Carver and a fellow that he met somewhere named Arnie Goldman, and I started the first electronic word processing company called Lexitron. And it had some degree of success. I have a picture or two of it. And the key idea of Lexitron, this was a concept sketch that was made by an industrial design firm that I think Carver will remember fondly called Zierhut, Vetter, and Shimano out in Burbank, some really talented guys. And this thing over here was the computer. This thing was an enormous box of electronics. And there was a display and the operator. And the idea was to make it work like a typewriter. So you had this electronic piece of paper. It was impossible to make a display that good. This guy named Niles Puckett, a Caltech student, figured out how to do that. This thing was about 3 miles long, this tube. It was electrostatically deflected and magnetically deflected. So it swept along. We drew little characters with it. And ridiculous. If you try and think about all the things that we thought we could do, this thing had about 2,000 integrated circuits in it. SSI was state of the art then. 2,000. Power supply weighed 150 pounds. It usually lasted a couple hours before it burst into flames. Memory was shift register. That was all there was. It was a big deal. Got it from that little company, Intel. Usually worked. This raster plus vector CRT. All this stuff we did in-house, made our own cassette drive because there was no other way. First machine had an MTBF of about 60 minutes, or 6 characters, whichever came first. The list price of this thing was $19,000 in 1972. To quote our very first customer, who was a consultant turning out reports about citing retail stores, he said, "You've got a machine I can't believe, from a company I've never heard of. It costs half a house, and you want me to buy it for cash?" The answer was, yes, sounds fair. Anyway, just so you can see, this was the concept sketch, and that's what it actually looked like. That was the real deal. So we really had kind of an idea of where we're going. It was certainly way before microprocessors, before MOS RAM. There's no suitable display, no adequate storage. We just built the whole thing. It was kind of ridiculous. But it all sprung from this whole history of trying to figure out how to do things and finding a need, and resulted in this thing. So, last slide. Many other interesting things also happened. I remember very well being removed from Carver's lab to the roof of steel after exploding a chlorine vessel in which we were trying to grow gallium telluride. For some reason, the safety department at Caltech thought it was okay to pollute all of Pasadena, just not to pollute the laboratory. But this is all true. I'm sure Carver will attest to this. Absolutely true. But that led Jerry Parker and I to find this location for building. He was into kayaking, what we thought was an innovative way to make a kayak. We were using chicken wire. It was a total disaster. But we built it over a few weekends on the roof. At any rate, it was a great 4 years. Thank you, Carver.
Well, there's some, can you hear me? Does that work? Yeah. In order to do the polywater, Steve, you can't sit down yet. In order to do the polywater work, it was important, as Steve said, to measure very thin layers of a very small amount of stuff. And to do that, we got our favorite machinist, Herb Adams, that we still work with today, even though he's retired, to build us a special fixture to do that work. And what it was a micrometer that has insulating extensions and then little gold electrodes on the two ends, and the one in the middle is insulated, so it came out on this. And we plugged that into the capacitance bridge. So this is what it made possible, measuring these, nanoliters that Barbie came up with. So Steve?
Boy, I forgot all about that. Cool.
I want you to have this.
Thank you so much. I really appreciate it.
Here's a box for it if you like.
Thank you.
The other thing, a story I'd like to share with you about Steve and Barbie is, Caltech was a stud farm for a long time. We had male students but no female students, and that made it a reasonably dismal place. And there was a faculty meeting in the 60s, I forget when. When did you get here, Steve?
I got here in fall '66, but I met you in '66.
Okay, so this was probably '67. It just turned out that the faculty was having this big meeting about admission of women undergraduates. And there were these guys that had never had a woman in their group or anything, but were pontificating about how this and that and the other would go wrong. And one of the things they were saying is, well, the women would feel so overwhelmed because they have all these men around and everything. So didn't quite compute for me, but so I sneaked out and called Barbie, and she was home. And I said, hey, Barbie, this is what these people are saying. And you were at MIT, where you were, what, it was 15%, I think, when you were at MIT. Yeah. And so you were pretty well outnumbered. How did it feel? And Barbie said, it was great. So I went back into the faculty meeting, and they were still huffing and puffing, you know. And I said, I have a data point. Turned out nobody else had any data whatsoever. So I reported, and it carried the day. Everybody laughed like hell, and we started admitting students. So in fact, you can thank Barbie for the first admission of women students to Caltech.